Hey guys, I've decided to switch up the topic for this week. I had considered missing out on skipping over, I guess, this idea of failure propagation and kind of going back and forth on it. I decided to come back to it and use that as this week's lecture. So, kind of relative to the schedule, you'll see reliability testing starting next week. So this week we will be covering failure propagation, as it's noted here on this slide. So to kind of lead into that, we've talked a lot about the engineering design process and a lot of the different things that are done throughout that process. Of course, this slide's kind of showing a couple of different systems here, and it's making the statement about safety, reliability, and affordability. And as we've seen a little bit in this class so far, and obviously as well in 3321, there are a variety of ways to get to a reliable system or a safety conscious system. And there's some of the methods that are shown kind of on the bottom of this slide. And with regards to failure propagation and kind of why I'm sticking it in here as opposed to previously, one of the challenges that I've seen with FMIAs and FMICAs is how to determine the effect of a failure. And, it's actually quite a big part of the analysis because the effect of the failure has a lot to do with the severity. And of course, the severity is a major part of the risk, and the risk is how we make decisions on the system. So if you think about that, knowing what the failure is and its severity or its effect on the system is very important in terms of ultimately creating a reliable design. And so that's essentially why I'm sticking failure propagation in here. So it's going to tie back to this, how we determine the effect within a FMIA or FMICA. This slide is showing a little bit more about the design process and just kind of motivating some of the earlier stages of design. The method that I'm going to present today is a little bit more geared toward early design, functional design. And so this is a little bit of a motivating slide. So it's kind of talking about the system requirements and design exploration. So essentially in the early stages of design, we're of course developing requirements which are shaping the rest of the design process. We're exploring solutions to those requirements and either functionally or after we have functions physically, what physical architecture we can have that meets a set of requirements. And really early in the design process, as we're developing these functional models and these physical architectures and behavioral diagrams, the design space is wide open. So there's a lot of flexibility in terms of how the system can ultimately meet that set of requirements. So one of the questions from an early design standpoint, and I know this a lot, you guys are all involved in design in some form or fashion. And I believe some of you guys are still actually living in some of the earlier stages of design. And in modern systems, that early stage of design tends to be quite short, and it also usually has a very limited number of people involved, and so it's kind of interesting in that way. But one of the questions becomes then, can we assess designs early on so that we can make more intelligent design decisions about which ones are the best, ultimately, which ones will move forward and provide us the best solution. One of the limitations to early design assessments, one, they typically don't exist, right? So we talked about FMIAs and FMICAs last week, and some of that was about functional FMIAs and FMICAs, and that's a good way to assess a design early on. And there tends to be a lot of uncertainty in that stage of design because a lot of times there isn't any data to support any sort of assessment. It's more logical. It's based on a lot of SME knowledge and based on their background. So there's a lot of incomplete and very uncertain knowledge. So again, the method that I'll present today is going to be used actually to better understand the system and how failures propagate through an early system so that we can then either one, use that information directly in a FMIA or FMICA, which is a very practical way to make use of the information, given that FMIAs and FMICAs are something that we are very in tune with as reliability engineers. Or thinking about the method today, later it's possible, instead of deploying the results directly in FMIA or FMICA, using them more directly with design. And so kind of circumventing the risk analysis, the traditional FMIA, FMICA, and using this method instead. I'm not going to propose which one's right or wrong. I think given this class, it might make the most sense to think about this as a better way to understand the failure effects within a FMIA or a FMICA. That's probably the most logical way to kind of think about what I'm going to present today. But I will open it up and just kind of say that that's of course not the only way that this method can be used. Okay, so the method that I'm going to discuss today is called FFIP, or the Function Failure Identification and Propagation Framework. Now this method is, again, it's used in early design around this time where we have functional architecture, so a functional block diagram and some basic idea what the physical architecture is, or if we don't have the actual physical architecture, if we can kind of hint at what we think it is at kind of a high level, that's going to be necessary. So again, it's used in very early design. So some of the critical needs that this helps to kind of understand is the functional failures that propagate through the system and what their paths are in that system. So how they propagate is one thing that this method is going to help to understand. It's going to help to understand, given a particular failure mode of a component, what's the loss in functionality. One of the big limitations of a component-based risk analysis is that it tends to help us, force us to focus on losing components as opposed to losing functionality. But it's important to remember that the physical form, the actual component, is just an implementation. It is just the physical item that's solving the function. But in fact, we design for functionality, because the functionality is really the need. And that's why the definition of failure has function in it, right? So the nice thing about this framework is it's going to direct the analyst toward what the actual lost functionality is. And it'll help to assess the impact of those functional failures as well. And it's all done, again, early in design. So FFIP developed as a conceptual design analysis tool that explores what types of failure scenarios there are and the effects on the overall system functionality, reasons about the effects and the causes. So this is kind of all built in, and uses high-level reasoning to map system behavior and interactions to the functional failures. And it does say, that last statement is before the design is realized, meaning before the actual physical architecture is defined. We have to have some basic idea of what that architecture is, but it's fairly high level, so it's still at the point in design where it's flexible. And that's how this tool was designed. It was designed more for early design, but it doesn't have to be only used for early design. It can be deployed later when there's more knowledge about the physical architecture as well. So it's still valuable. Because I understand that not all of you guys are currently at that point, but hopefully at some point you'll be at that point of design. In this, so if this isn't useful now, hopefully it will be later. So this slide's presented as a task, and essentially I'm going to walk through this in just a minute. So given the functional and physical architecture, so the configuration model or configuration flow graph is the physical architecture. So given the functional and physical architecture of a spacecraft system, and then the critical event scenarios or a list of failure modes, can you find the potential functional failures and the propagation paths. So this is kind of an example of what what we might specifically be able to do with something like FFIP. Take the physical, functional architecture, some knowledge about how the system works in a basic way, and a list of failures, and a list of component failures, right? So things we can look up. And given that information, can we find the functional failures, so what functions in the system are lost, as well as the actual propagation paths that led to those, right? Because the propagation paths are something that are often not directly thought about. The issue with not thinking about the propagation paths is that propagation paths are actually something that we can mitigate, right? So if we know what the propagation path is from a design standpoint, and this isn't usually what the reliability engineer does, but they gain the knowledge of what the propagation paths are, but given those, they can turn those over to the program, and the right person can say, I understand how this propagates, and I understand what you've done to determine how this propagates, and as a result, I can eliminate that propagation path by making a change to the system. So it's not usually the reliability engineer that proposes that change, but it's the reliability engineer that would determine how that propagation occurs, right? And it's often across multiple systems, and between mechanical and electrical, between sensors and other physical parts of the system. So it tends to bridge gaps between what other engineers see as their part of the system. So let's talk just a little bit about failure propagation for a minute. The diagram here shows the same system. This is just a kind of a fictitious type system. Same system in multiple instances. And essentially what you're seeing, starting from the left side going to the right side, is initially the system is nominal. And from A to B, there's some sort of failure in the diesel tank, which is represented with this yellow square. And so traditionally with FMEA, this is essentially what we would do. We would say, okay, something has failed, and at B, step B, we would say, okay, what's the effect of this failure, right? And now it's on the individual to reason about what the effect of the failure is. And in a simple example, this may not be that challenging, but of course, most of you guys are developing very complex systems. There are torpedoes or other weapon systems, or submarines, or aircrafts. There's a variety of different systems. It very quickly becomes impossible to reason about the true effect of a failure when the system becomes complex. And it doesn't actually take very much complexity to get to that point. That's why we model things using a computer. Okay, so that's kind of the importance of the failure propagations. At step B, this is typically where we go off and reason ourselves, and instead we'd like to use some sort of framework to help us reason about what the effect of that failure is. So from B to C and D, we can see that the generator then is taken out. It's essentially failed next, and then finally the water pump. And then in E, it doesn't seem that the actual failure has been lost, and the other diesel tank is supplying the generator. And so these are two different scenarios, but the basic idea here is that kind of going from A to B to C to D, we can see that there's this progression of the failure moving throughout the system. And it doesn't always have to mean that, for example, the diesel generator has failed. It doesn't maybe have a fundamental failure mode, but if it doesn't work, then that's how we kind of define this propagation of a failure, right? So if the generator needs some sort of diesel fuel to run, and the diesel tank has failed, then the diesel generator can't function anymore. It's essentially lost, right? And if the diesel generator is not working, it can't operate the pump, right? So then the pump's useless. So that's the idea of failure propagation. It doesn't have to be that we're not looking at each item individually failing on its own. We're looking at an initial failure starting and how that propagates throughout the system and what functionality is lost as a result of that. So I'll use another just very quick motivating example here of a reaction control system. And what I'm showing here on the left side is the functional model. and what's on the right side is the physical implementation of that functional model. And I don't want to actually go into detail on this because that's not the point. The point here is that what this is essentially showing is we would say if a component fails, what's the lost functionality to the system? And this very brief, very basic example shows the couple of functions that are lost, and actually what it doesn't show actually is the sequence of those lost functions on the right side where there's the x's, where one occurs and then the next occurs and the next occurs, and it's sort of trying to display this time-based loss, but what it's really showing is kind of just the individual functions that are lost. And so, but again, the idea here, without going into detail on this example, is that a particular failure occurs and the function that that's associated with, of course, fails first, but then other functionality is lost as time progresses. Okay, so those are a couple of brief introduction slides that are being used to motivate this example, this FFIP methodology. And so what I'm going to do now is explain it in a little bit more detail, the actual methodology and how it works. And then what I'm going to do next is then go in and provide an example. And then you guys will have a homework assignment on this as well. I'm not actually going to have you build the FFIP models. Instead, I'm going to have you guys actually interpret the results of them to reduce a little bit of the complexity of building the models, because that's not really the intent of this class. But interpreting the results is actually very important. So that's the plan for you guys for the homework. The basic model shown here is the architecture of FFIP. And you'll notice that there are kind of three different sections to this. So the first is the system model section, which is what's actually circled in the red circle. The second element is the behavior simulation. And the third is the function failure logic, or the FFL. So what I'm going to do next is run through each of these sections individually. But let's first kind of introduce an example, so we have a running example to learn this with. And that is of this tank system here. So there's there's 7 different components involved here. There's of course a tank in the middle. The tank has a height level, which is indicated with the dotted lines on the right side. There's an inlet pipe as well as an inlet valve. There's an outlet pipe and an outlet valve. And then there is a sensor that's measuring the height of the water and a controller that will essentially open the inlet valve and the outlet valve based on the height of the water. So ultimately it's a fairly straightforward system, and again, it's a control system too, so it's actively looking for the height of the water within the tank so it can make decisions based off that. So first off, in terms of the first portion of FFIP within that large systems model box, there were several, in fact, I'll go back and look at it. So there are several different individual models that we need to discuss: the functional model, the configuration model, and the component behavioral model. So we're familiar with the functional model. We discussed this in SE4321. I'm showing the functional model for the example here. So we have liquid coming in, it's being imported, guided, transferred, stored, right? So for example, the store liquid is the tank, right? It's supplied and transferred, guided, and exported. And then you can see on the bottom side right here that there are functions for the control aspect of the system, right? So again, the functional representation is going to tell you what the system is intended to do. It doesn't tell you how it does it, but it tells you what it's intended to do. And in this case, we have, in terms of the flows in the system, we have liquid, right, which is a type of material, and then we have the control and status, which is a type of signal. And the next element of the system model is the configuration representation. There's a couple different names that this kind of goes by. Configuration flow graph is the way that this methodology kind of defines it. But the configuration flow graph is just a physical representation of the system. And it uses graph because of network theory and graph theory. It's nodes and edges. But essentially what you need to understand here is that these are the actual components that solve the functions of the system, right? And so we can see things like the inlet valve, the inlet pipe, the tank, the outlet pipe, the outlet valve, the sensor, and the controller. And those are the 7 components of the system. This slide here shows that there's a relationship between the functions and the components of the system. This is important because in FFIP, there has to be a mapping between the two because the failures are implemented based on the components, but they are used then to reason about the functions of the system that are lost. But from a design standpoint, this actually makes sense because the physical side of the modeling is the implementation of the functional side, right? And the functional side is what ties to the needs and the requirements. And so kind of naturally matches the design process, right? So for example, in this particular case, the tank implements the store and supply liquid functions. Similarly, the inlet valve implements the import liquid and guide liquid functions. Okay, so now the third and final part of the first section of the methodology is the behavioral representation. So this might be the kind of the newer part, stuff that you guys are a little bit less familiar with. So it's the qualitative behavior models, or the models, the behavior models here are these qualitative type of models. They are represented here as finite state machines, meaning that they're in a particular state, whether that's nominal states or failed states. So for a pipe, we can say, for example, a pipe could be nominal, it can be failed clogged, or it can be failed leaking. In terms of the component behavioral models, each component mode is actually modeled separately, which we'll see here in just a second. Behavior in each mode is derived from the input and output relationships. And then the state variables that are critical to the system behavior are actually associated with these CFG flows, the flows in the physical architecture, and they're tracked explicitly. So there's some examples here of things like flow rate, pressure, temperature, things like that. It's important to understand that the components can switch between modes either nominally or in a failed sort of way. So, for example, a valve can be nominally open and it can be nominally closed, but it can also be failed open and failed closed. And so that's kind of an important distinction. So the mode transition diagram that's represented on the bottom left of the slide essentially shows that information. All right, I'm resuming the lecture slides after having to stop for a second. Someone came to my door. I apologize. The diagram on the bottom left shows the different modes of the valve, where again there's nominal on, nominal off, and then failed open, failed closed. So to transition between nominal on and nominal off, it's a standard situation, right? So the command, either a person can turn the valve from on and off, or some sort of software, control software, in our case, can also do that. And so that's how we transition. You know, for example, from nominal on to nominal off, it's commanded closed. Whereas to go from either one of the top two states to either one of the bottom two states, it has to fail, right? So that's kind of the distinction there. So it's of course, nominal on, meaning it's open, is the same actual state as failed open, except one's failed and one's not. So there's the distinction there. The behavior model on the bottom right side shows the actual behavior that goes along with each of these states. So for example, for nominal on, in the valve, the pressure in the liquid in equal the pressure in the liquid out. For a failed closed situation, the flow in is going to be 0, the flow out will be 0, the pressure in and the pressure out are also 0. Right? And then in a nominal off, it's the same scenario. The flow in and out and the pressure in and out are also 0. And in a failed open, the flow in and the flow out are the same, and the pressure in and the pressure out are the same. So what you might notice is that failed open and nominal open actually have the same behavior as well as failed closed and nominal off. Which makes sense because they're, again, the same state, except that one's failed and one's nominal. So once we're in a failed closed state, we cannot command it to go back to nominal on. And that's something that you'll notice in this diagram down here. Once in a failed state, it's stuck in a failed state, which essentially represents, at that point, some maintenance would need to be done. But we can't, in this particular case, we can switch through these and transition down to a failed state. But once in a failed state, we cannot go back to a nominal state. Okay, these equations will be important here in a little while, as well as this diagram here. So these will come back in a different form here in a little while. So the next element of this framework or methodology is the behavior simulation portion, which is going to use all of the system model information we've already discussed. Okay, the behavioral simulator is essentially the model where the individual component behavior models and system logic are all integrated together. So it's essentially taking all the different models previously and kind of making sense out of them. The objective of this element of FFIP, the behavior simulation, is to determine the system behavior under the occurrence of events that cause specific component mode transitions. Okay, so we're looking for failed items. We're looking for failed functions. Okay. What you're seeing down on the bottom left in the state variable box, this box here, is the different variables that are associated with the system and what their different values can be. For example, a liquid flow can either be 0, it can be low, it can be nominal, or it can be high. So notice that this particular methodology does not understand essentially the details or the values of the specific flow, right? Because we're pretty early in design, and so the flow rate, actual value of flow rate, is not actually used in this methodology. Instead, we're looking at, is it high, is it low, is it 0, or is it what it's supposed to be? So that's an important distinction. These state variables are determined based on what the components and functionality of the system are, right? So we don't know that we're interested in flow rate or liquid flow unless we have some sort of liquid in the system, right? So that's important. So that's one way in which the behavioral simulation uses the system models. On the top right, this box here, the control laws, this essentially takes the information in the state variables and how the system is supposed to work and develops some laws or equations to make sure that the control is working correctly. So obviously in a situation where we didn't have any sort of control, like in the flashlight for the previous homework assignment, these control laws wouldn't exist. But essentially what they say is turn a control signal on. There's control signal 1 and 2, which are associated with valves 1 and 2. So turn a control signal on given that a particular value is met. So if the height reaches the top, then we of course would want to pump some liquid out. So the output valve control signal turns on. And if it goes down below a certain threshold value, that would turn off. And if it gets even further down, then the other control signal turns on to fill it up. So essentially, it's controlling the level of the water and trying to keep it, level of the liquid and trying to keep it somewhere within a boundary.